So back when we were first learning about how to solve systems of equations via the method of elimination, back when we were first learning how to do row reduction, we said that there were three actions that we take as we are solving the system, which correspond to three actions that we perform when we are row reducing the matrix. And those three actions were called elementary row operations. The three elementary row operations were: the first thing that you can do is swap the rows in your matrix, or equivalently, swap the equations in your system. The second elementary row operation is you can scale a row in your matrix, or equivalently, you can scale one of the equations in your system. And the third elementary row operation that we performed as we were solving systems is to take one of the equations in the system and add it to one of the other equations, or equivalently to take one of the rows of the matrix and add it to another row of the matrix. These were the three elementary row operations that we performed when row reducing a matrix. In this lesson, we're going to learn about something which is called an elementary matrix. And an elementary matrix is a matrix which encodes these elementary row operations. Let me give you an example of what I mean. I claim that this matrix right here, 0, 1, 0, 1, 0, 0, and 0, 0, 1, is a matrix which encodes the action of swapping row number 1 with row number 2. And in particular, what I mean is that if you take any matrix, and if I multiply this guy on the left, I claim that this left multiplication will have the effect of swapping rows 1 and 2 of this matrix. So let me prove that to you. If I'm going to calculate this matrix product, I'll start by doing this first row times this first column. First row times first column will give me the result 2. Then first row, second column, that dot product would give me a 4. First row, third column, that dot product would give me a result of 0. Then as I move to the next row, row times column would give me the result 3. Row times column would give me the result of 1. Row dotted with column would give me the result of 5. And then as I do the final set of dot products, row times column returning a value of 1. Row times column returning a value of 7. And row times column returning a value of 2. So sure enough, as I have claimed, left multiplying by this matrix has had the effect of swapping rows 1 and 2 of this other matrix. Here is another matrix which encodes a certain elementary row operation. This matrix here, 1, 0, 0, 5, I claim, has the effect of taking another matrix and scaling its second row by a factor of 5. So to support that claim, let me go ahead and perform that action on an example matrix like 3, 1, minus 1, 2. If I perform this matrix multiplication using the normal algorithm, row times column, that first row times that first column would give me a value of 3. This first row times this second column would give me a value of 1. This second row times this first column would give me a value of minus 5. And then this bottom row times this final column would give me a value of 10. So just as claimed, this bottom row of the matrix has been multiplied by a factor of 5. So this matrix has encoded the action of scaling the second row of a matrix by a factor of 5. For one final example, I claim that this matrix right here, 1, 0, 0, 0, 1, 0, and 1, 0, 1, I claim that this matrix performs the action of adding row number 1 into
row 3.
So to verify that claim, let me take a 3 by 3 matrix with whatever entries 1, 2, 4, 0, 2, 5, negative 1, 3, 0. Let me left multiply that matrix, and let's verify that the effect will be to add a copy of row 1 into row number 3. So if I perform the necessary dot products, this row times this column is going to get me a value of 1 in the top position. This row times this column is going to get me a value of 2. First row times the third column is going to get me a value of 4. Second row, first column will get me a value of 0. Second row, second column will give me a value of 2. Second row, third column will give me a value of 5. And then row 3 is where things start to get interesting. If I apply this row to the first column, I get 1 times 1 plus 1 times negative 1, result 0. If I apply the third row to the second column, I get 2 plus 3, 2 plus 3 being 5. And if I apply that final row to the third column, I get 4 plus 0, 4 plus 0 being 4. And so, indeed, what I can see is that I have had the exact same effect upon the matrix as if I had added row 1 into row 3. So the elementary row operations that we've learned earlier in this class can be encoded in matrices and in matrix multiplication. And the matrix that encodes an elementary row operation is called an elementary matrix appropriately. Now, if you want to find the elementary matrix that encodes a certain row operation, all you have to do is perform that operation on the identity matrix. Let me give you an example of what I mean. I'm trying to find a matrix that would encode the action of taking a matrix with 4 rows and swapping row 2 with row 4. So if I want to encode that action, I'm going to start with the identity matrix that has 4 rows and 4 columns. I'm starting with a matrix of this size because the matrix would have to be 4 by 4 in order to left multiply a matrix with 4 rows. So starting with the 4 by 4 identity matrix, I'm now going to perform this action on this identity. I'm going to take this identity matrix and I'm going to swap row 2 and row 4. And that action performed on the identity matrix is going to get me 1, 0, 0, 0. Then 0, 0, 0, 1. The third row is unaffected, but now the fourth row has become 0, 1, 0, 0. This would be the elementary matrix that encodes this action. This would be the matrix which, when multiplied, will swap rows 2 and 4 of another matrix. There's a special name for matrices that swap rows in particular. You sometimes hear these referred to as permutation matrices. Let me do another example. I want to find a matrix that encodes this action of adding 2 times row 1 into
row 3.
So since I'm trying to perform an action on another matrix that has 3 rows, I'm going to start by building the 3 by 3 identity matrix. Having created the 3 by 3 identity matrix, I'm now going to perform this action on that identity. And I'm going to add 2 copies of row number 1 into row number 3. So that is going to change row number 3 to now
2,
0, 1. And so this would be the elementary matrix that encodes this action, adding 2 copies of row number 1 into row number 3. Now, when we row reduce a matrix, we often perform a sequence of row operations. For example, you might start by swapping two rows, and then you might scale a row. So how would we encode successive row operations using elementary matrices? So for example, first swapping row 3 and row 1, and then subsequently adding
-3 times
row number 1 into row number 2. So I'm going to start by finding the elementary matrix that represents this first step here. To swap rows 1 and 3 of a matrix with 3 rows, I would start with the 3 by 3 identity, and then I would perform this action on this identity matrix. So that would give me 0, 0, 1, it would give me 0, 1, 0, and it would give me 1, 0, 0. This is the elementary matrix that represents this first step in this two-step process. Now, if I wanted to encode the second step, I would have to start again with the 3 by 3 identity matrix, and then I would have to perform this action on the identity. So add -3 copies of row 1 into row number 2, and that's going to turn the identity into 1, 0, 0, -3, 1, 0, and 0, 0, 1. So now that we have the two matrices that represent performing these two actions separately, let's now think about what would be involved in performing this action first and this action second. For convenience, let me go ahead and call this first elementary matrix E1. And let me call this second elementary matrix E2. If I wanted to take another matrix A and I wanted to perform this first step of swapping rows 3 and 1, the first thing I would do is I would left multiply that matrix by the E1 that I found earlier. If I then wanted to perform this second step of adding -3 copies of row 1 into row 2, I would then left multiply this result by the second elementary matrix E2. So all this to say that if you want to perform two elementary row operations back to back, this product, this matrix right here, E1 times E2, represents the two steps taken in sequence. So start by multiplying on the left by E1, and then multiply again on the left by E2. I want to make an observation about the elementary matrices. I want to observe that each of the elementary matrices is actually invertible. And to see that the elementary matrices are invertible, and actually to get a sense of what the inverse of such a matrix might be, let's think about the elementary matrices from the perspective of what action they are performing. Remember that an invertible matrix is a matrix whose action or whose effect can be reversed. And the inverse is the matrix that reverses that effect. So for example, if you wanted to find a matrix that has the effect of taking a matrix with 3 rows and swapping row 1 and row 2, if I wanted to find the matrix representing this elementary row operation, all I had to do was start with the identity matrix of the appropriate size and perform this same action on that identity matrix, 0, 1, 0, 1, 0, 0, and 0, 0, 1. So this would be the elementary matrix that encodes this action. To reverse the effect of the matrix E, all you have to do is swap row 1 and row 2 again. And that will swap them back into position. In other words, the inverse of the matrix E is just equal to the original matrix itself. Because if you want to reverse what the original matrix did, all you have to do is perform the action of the matrix a second time and swap row 1 and row 2 back into position. So this is what the inverse of a permutation matrix looks like. Permutation matrices that swap rows are pretty special because they are equal to their own inverse. Because you can reverse the effect of E by just applying E again. Let me give you another example of an elementary matrix and its inverse. Let me suppose that I am writing down the elementary matrix that encodes this action of adding
-2 times
row number 1 into row number 2. So to find the elementary matrix representing this kind of action as performed on matrices with 3 rows, I just need to start with the 3 by 3 identity and perform this action on that identity. So that's going to give me 1, 0, 0. And then I'm going to add -2 copies of the first row down into the second. And so this object here, 1, 0, 0, -2, 1, 0, and 0, 0, 1 would be the elementary matrix representing this action. So let's think about what we would have to do to reverse or undo the action performed by E. Well, if E is performing the action of subtracting 2 copies of row number 1, I should be able to reverse that action by adding 2 copies of row number 1. Instead of adding -2 times row 1, I'll add +2 times row 1 into the second row of the matrix. And that should undo the action performed by E. So to find E inverse, all I would have to do is write down the matrix that reflects this action. And using the same process as before, the matrix that represents this reverse action is +2, 1, 0 in the second row, as opposed to -2, 1, 0 in the second row. So this would be the matrix that represents E inverse in this case. That concludes today's video. In today's video, we remembered what are the elementary row operations performed on systems and on matrices when you're doing row reduction. And we found that each of those elementary row operations can be encoded in a matrix, appropriately called an elementary matrix. Left multiplying by an elementary matrix has the effect of performing that row operation. The elementary matrix corresponding to any particular row operation can be found by just performing that operation on the identity. Start with the identity, perform that operation on the identity, and that will give you the matrix encoding that operation.